indicates how the frequency deviation in Indian grid system has uh, progressed over the years. So you can find that in the recent years, the frequency deviation around the nominal value has remained in a narrow range. So it means that it indicates that we have been able to apply an effective power regulation in the national grid level, right? So with this, we move to the next slide. Here, this slide will have some information about how the frequency dynamics is related to the system. And this is mainly we refer from the swing equation. As you can see, you and uh, generation, so that you can say, let's say the scheduled amount of active power to be generated by the turbine generator unit. Then you have the soft power from the turbine, and then the generator is connected to the electrical load here. So from the swing equation that you have the relationship the df by dt. So this is the most common or the basic swing equation. F naught is the base frequency, so it could be the nominal frequency, which is of 50 hertz, and H is the inertia of the system, that is of a turbine generator unit, combined turbine generator unit inertia. Then the power which is from the generator side, then the power which is on the load side, we can say, and the this is the apparent power, the rated MVA of the turbine generator unit. So we have this division in the term, so that we are able to have the change rate of change of frequency uh, as a per unit form. So we have this term. So thus you can see the rate of change of frequency will depend upon what is the amount of disturbance, what is the active power being generated by the turbine generator unit, and what is the amount of the load change here. So the difference, this difference will decide how does the frequency will change. And also this part, you can see that it also depends on what is the inertia of the system. So thus the rate of change of frequency will be determined by what is the inertia and what is the amount of load or the power, the disturbance, you can say here, right? Because if I say a step disturbance in the applied load, right, then at that instant of time, the power from the output power from the generator is constant at that instant. So for a step load disturbance, so this will result into a deviation or the amount of disturbance between the power output from the generator and the load disturbance here, right? Next, now, as I said that what are the factors that affects the change, the frequency change, and that is say as frequency decay. So one is the, as I said in the previous slide, one is the difference of the power that is your delta change, delta power change here. Another term is the inertia. Right. So these are the important terms which are the influencing factors for the frequency decay. Then in this term, we have not included the load damping constant here, but if you have the dynamic loads, so those dynamic loads, let's say induction motors as a load, so uh, there they are in fact frequency dependent loads in fact, and thus they provide a damping torque, and but this is not included in the term as given here. So altogether these are the three factors which will decide how does the frequency, this rate of change of frequency will change. uh, Now, in terms of the frequency control for the frequency regulation, we will discuss more in detail later on in the later slides. Normally, you have two approach. One is that if there is a load, let's say you have a load increase, right? And if you feel that you have sufficient power that could be generated out of the available capacity of the generators, so including the spinning reserve capacity in the power plant or in the complete network, it is possible to have the increase in the power generation, and that could be achieved by governor action. This is one way, and this normally we apply against the increase of the load demand, you can say. We apply the governor action even when you have a load decrease, but uh, if in case, if we refer to this term, the approach referred as load setting. If in case it is felt that because of the load increase, the available capacity of the power generation, including the spinning reserve, cannot be met against the increased demand, then we have to apply this approach for regulating the frequency. Because when we have a load increase, and if you feel that if the system operator feel that they think that you don't have capacity for more power generation against the increased demand, then in that case they will apply some kind of action depending upon the change in the frequency deviation against the increased load demand. The amount of load would be frequency deviation amount or certain percent. It is all again the policy, regulating policy, and again it differs in the system actually. Maybe in some of the slides I will show you how we have the this approach being applied. That means how much change in the frequency, so what should be the change in the load, what should be the percentage change in the load, or that means the load cutout. So this load setting we apply whenever we feel that the generation cannot be met against the increased demand here. So in general, these are the two principles for frequency control or frequency regulation that we apply in the network here. Anything on this part? So we move to the next one. Yeah. Now here, if I consider the load change influence, this part here, this one. How does the load change will influence the frequency deviation? So this load change is the, as I said, it is the difference of the demand, active power demand, and the active power generated by the machine. And you can say that it could be as a percentage of power generation here. Now, as I said, the greater the change, greater this change, delta P, greater will be the rate of frequency decay. So that means the rate at which the frequency will decay, it will be much more, you can say. And if it is a isolated system, so that means, let's say you have some power plants, and you have some local load, but your power plants, one or two power plants and your local load, they are not connected to a large network, main electricity grid. If they are not connected, that means the system operates as an isolated one, let's say. Then the change in the load, uh, it will tend to be a larger for frequency deviation. So in that situation, whenever you have a change in the load, it will result to a larger uh, change or the larger decay of frequency variation, you can say. So thus, for an isolated system, it is more critical, it is more serious issue whenever you have a load change, because in that case, the decay of the frequency will be much more. Yeah. I maybe here you can see more clearly from the graph as shown. So how does the load change will influence the decay of frequency? So now here this on the y-axis you have the frequency, and on x-axis it is the time in seconds. And thus the decay of the frequency, that means the fall, the initial rate of fall or the decay of frequency change. If this is the amount of the load change, we are all talking about, remember, there is a fall in the frequency. So frequency will fall from the nominal value whenever you have an overloading. That means you have an increase in the load, right? And these plots have been shown for a given inertia constant and load damping constant here. So because we want delta x, so for a small amount of load increase here, right, the decay of the frequency, you can say it is much slower. But if you increase the load in, that means if you have more 30%, in fact it is 30% overload, what is the change in the frequency? Similarly, if you have 50% increase in the load, the decay is much sharper here. And if I say suddenly you have a 100% increase in the load, let's say your at a given instant, right, your frequency was 50 hertz at a given instant, let's say frequency was 50 hertz, and in that case your generation match with the load, right? And let us assume that your generation was 1000 megawatt and your load was also 1000 megawatt, and in that case frequency was maintained to the nominal value of 50 hertz. And at another instant of time, you have a sudden increase in the load to 2000 megawatt. So this is 100% overloading. Now sudden, you have a sudden increase, suddenly you have 100% overloading to 2000 megawatt. Then in that case you can see that the decay in the frequency is much sharper, it is much more, and again the frequency drops to 40 hertz in 6 seconds something. So if in case you have a 100% overloading, then in that case there cannot be any way by which you are able to maintain frequency within the narrow range of frequency, no, nominal frequency, because in 6 seconds you can say the frequency will drop to 40 hertz, and thus in that situation all the generators will get tripped, the synchronism will be lost because in 6 seconds you have to act upon. Thus it is very important that against the overloading, this change in the frequency which you observe, which you have it, because even in the case of 10% overloading, frequency drops to 48 hertz here with this also, because we want because if I say 5% plus minus 5%, so this change will be 47.5 here, right? So that is the, but if I say 2%, then it will be much narrow band of frequency regulation. So you can see here that the load change has much significant influence on the decay of the frequency here, right? Anything more, right?
Sir, this effect is more pronounced in the isolated system. Is it because that the power difference can't be compensated from other areas by making power flow from other areas?
No, I'm not saying, I didn't say anything that this discussion is for isolated. I didn't say anything. This is in general. This is in general. All right. Maybe because if you have an isolated system, the decay may be more sharper. That could be possible. But these plots again, these plots will depend upon what is H, what is D as well, right? So though these plots are for a given H and for a given D actually. Okay. Then we will have later on in the later slides. How does the inertia influence the frequency? So at the moment, we are analyzing the decay of frequency with the load change, right? So here, this analysis is for given H and D here. But altogether, in a system, you have the inertia, you have the D, you have the load change. So all three will play their respective role to vary the frequency. All the three will play their respective role. Okay.
Okay, sir.
Excuse me, sir.
Yes.
Sir, yeah, here you have used d equals to 2. So, what does this signify?
Uh, it is load damping constant. It is in per unit, right? So it says that how much change in the frequency will occur to the corresponding change in the power, we can say. That is the how we have defined the D actually, load
Okay, sir.
damping constant.
Yes.
So next factor that influence the frequency variation is the inertia, and this is the combined inertia of turbine generator unit. Now this will determine what is the initial rate of decay for a given load, for a given overload, you can say. So smaller the inertia, the more will be the decay of frequency, right? So you can see here that if you have an isolated system or if you have an interconnected system, so in case of an isolated system, inertia will be lower, right? But if you have an interconnected system, inertia will be comparatively larger. And thus, for the same amount of load change in an isolated system, the decay of the frequency will be sharper, it will be faster. However, for an interconnected system, Since the inertia is comparatively more, then the decay in the frequency will be slower, you can say. I mean, the slope of the decay, slope of the frequency change, it will not be that sharp. And this is what it says. It's for an isolated system. And isolated system will have a smaller inertia. And thus, for their case, the decay in the frequency will be much more sharper here. As you can see in this slide here. Now, we want to understand how does the inertia affects. So we will consider 50% load change here. And D is 2. And we have different value of H, 2, 4, and 7 second. So you can see here that for a load change, for a load increase of overloading of 50%, if the H is 2 second, the frequency decay is sharper here. So that means the frequency drops to 42 hertz something in 6 seconds something, right? However, if you have more inertia, higher inertia, then the drop in the frequency, it is slower. The slope of the frequency decay, it is not so significant comparatively. And similarly, if you have much more inertia, for the same increase in the load in percentage, you can see that the drop in the frequency is still slower. So that means you have this much time. This is which is now which is in with you to operate, to regulate the frequency back to the nominal value. So so that means this initial decay will depend upon H, and then again this change will depend upon D, which I have not indicated here. So overall frequency will drop, it will decay, and then it will change because of D, and then it can be maintained around the nominal value, but it will be again through the governor action. So altogether, it is the inertia and the amount of the load change that gives you a sufficient time to regulate the frequency back to the nominal range, I can say here. Maybe in one or two slides, I have this part. I think, okay, yeah, it is somewhere here. Okay, right. So third factor, which we have it here, load self-regulation. As I said, that is the load damping constant here. So as we have the frequency decay, the system demand decreases. If you remember, we have said that the induction motors. So if you have the drop in the frequency, right? If you have the drop in the frequency, the power drawn, the power drawn by the machine, induction machine, the torque, you can say torque reduces, and thus the power drawn by the machine reduces. So in one way, you have actually a self-regulation action by the induction machine to improve the frequency towards the nominal value, I can say, in other words, right? So that's why it is referred as self-regulation by the dynamic loads here. So, and right, it could be mainly from the motor loads here. And this is how they are related. So you can see that change in the P, change in the load. So as I said that D has, we define the D in per unit actually, right? A constant value. So it is the per unit power and it is the per unit frequency here. So you can say what will be the load damping constant here, the per unit power to the per unit frequency change here. So now let us see how does the D influence the frequency here. So this is again for a given H parameters. So you can see that for different amount of D, if you have a smaller D, smaller self-regulation from the induction motors, let's say, then the drop in the frequency here, right? But if you have more higher D, if you are, let's say, if let's say if most of the load connected to the machine, connected to the generator, they are of induction motor types, let's say, rather than let's say the lighting loads, because lighting loads, they are the static loads. So if you have more induction motor loads, then in that case you will see that the drop in the slower. And this is how the load damping constant uh, you will it will self regulate, and thus it will minimize the decay of the frequency. So in one way, because of the self regulation from the dynamic loads, uh, the drop in the frequency can be slower. It can be slower and if you have more dynamic loads in the system, right? And that's why it is very important that in your network you have some of the loads as induction motors, right? So if you don't have induction motors as a load, then the frequency regulation will be a serious issue. It will be a serious issue that if, let's say, you just have lighting load. If you just have lighting load, let's say 100% of the load, out of the 100% of the load, if I say that if I say that 80% of the load, they are static loads, lighting loads. So the 20% remaining 20% load are the motor loads. Then in that case, frequency regulation will be a challenging. But if I say 70% of the load or near about 80% of the load, they are of as dynamic loads, then self-regulation can take place here, and thus it will not be a serious issue in the frequency regulation through the governor action. It will not be, because in that case the decay of the frequency will not be that sharp here, right? So what should be the purpose of frequency control? Because we want a balance between the demand and the power which is available, which is generated here. And this balance between the demand and the generation, it is reflected in terms of frequency variation. So now active power difference, in fact deficit you can say, because that means you have uh, more demand and less generation. So if I say active power deficit will cause a frequency drop. Yeah. And as you can see here, there are two plots. So this is the decay in the frequency here. And we have two plots here. So first plot is without regulation. And second plot is with regulation. So if you don't have any governor action or anything, right? So whenever you have a load increase, because you have active power deficit, frequency will drop and then it will settle down to some steady state value here, right? So in that case, this is the residual frequency change, you can say, right? Now if you apply some regulation to the governor action and so on, then it will be possible that you are able, because let's say because you had a sudden load increase, okay, and because of the sudden load increase, the frequency drops, but this decay in the frequency will depend upon what is the inertia and then and other influencing factors here, right? But this change in fact more or less by self-regulation here, right? This part is by self-regulation. that we can met out of dynamic loads here. And then because there you have self-regulation and then regulation through your governor action. So with the regulation applied, it is now possible to get the frequency change, get the frequency value in the narrow range. That means towards the nominal value. It is possible. You can get it here, right? Anything? We will discuss more in detail on this part. We have some derivation of the equations also. So as I said here, if you don't have regulation, so and if there is a loss of 10% generation, yeah, it is also possible that suddenly one of the generator fails, right? You have a constant load, right? You have a constant load, you have a constant demand, but generation has suddenly reduced, right? Then this will result into a drop in the frequency in this range uh, within a minutes. And this drop in the frequency, as I said, it will depend upon what is the inertia and so on. So you can see here that within minute, uh, 10% disturbance, because loss of 10% generation means you have 10% del p power, active power change. So that may result into frequency drop in this range. However, typically, the maximum allowed frequency deviation, it is in this range, zero point 0.1 hertz to zero point 0.2 hertz. And thus, if you want to maintain the frequency deviation in this range around the nominal value, then we need the regulation in the system, frequency regulation in the system. And how we achieve the frequency control, and that is through the governor action. And this is through the governor action, and that is by automatic control of power. So as I said, I think in the earlier slides that we applied two approaches for frequency regulation. One is through the governor action, right? And that will be how effective we are able to match the generation against the load and thereby maintain the frequency. This is one way. Second way is that if you feel that you are not able to meet the demand, increased demand by the available generation, including the spinning reserve, then in that case, we have the use of automatic relays actually. And these relays, they are actually tuned to automatically cut out the load in a discrete form. So if I say that 0.5 percentage change in the frequency, that drop, in fact, it is the load setting. So left is, if I say 0.5 percentage drop in the frequency, so let's say 5% drop in the 5% load to be cut off. If at another instant of time, if we feel that there is a drop in the frequency by 0.2%, then we say that okay, 8% load cut out. And then another instant we feel that okay, still we are not able to get the frequency in a narrow range. Then we feel that okay, we have 0.3% drop in the frequency, so 10% load cutout. So depending upon how much drop in the frequency takes place, so step by step in a discrete form, all right, in a step by step in a discrete form, we have an automatic cutout of the load here. And this will, and adopting this approach, will prevent the collapse of the system, because we know that okay, this much amount of the load increase took place, and if we are able to apply a load shedding, then in that case we can avoid the system failure. That means instability can be avoided if we apply load setting approach. In some cases we do that. So now so now for with those discussions, it is clear that active power regulation, it is reflected in terms of the frequency here, and thus the frequency signal is frequency signal. It will depend upon the balance, active power balance in the system, and whenever you have a change in the real power, it will affect the system frequency. And as such, you can say that frequency could be a common factor throughout the system uh, to tell you how to tell you whether there is a mismatch in the active power in the system or not. So if there exists a active power mismatch, that means if there exists a delta P, that means the difference between the generation and the demand. If there exists a difference between the generation and the demand, that could be reflected in terms of frequency. Yeah. So it is the frequency information that tells you whether you have perfect match of the power or not. Yeah, right. So now, in a interconnected system, when we have two or more areas, because if there could be one area, let's say it could be the regional grids, right? So we have several regional grids. So one area, a regional grid being connected to another regional grids. So in an interconnected system with two or more independent control areas, in addition to the frequency control, generation within each area has to be controlled, and that will be according to the scheduled power exchange. So that means in a interconnected system, apart from frequency regulation, apart from frequency regulation, we are also concerned about how much should be the power flow in the tie line that connects the two areas, right? And thus, as if you remember earlier, we had the term load frequency control and automatic generation control. So the control of the frequency, this will be part of the load frequency control. But if you talk about the control of scheduled power flow, then in addition to this LFC, if in case you have a scheduled power flow included, then it will become AGC, automatic generation control. So in the active power balance, it is not only the frequency control, but in some cases we also have the regulation as per the scheduled power flow. So both are included in the system for active power balance or active power control here. Now, since you have several generators which will supply power to the system, and out of those several generators, some of the generators can be provided to allocate the change in the demand. Remember one thing, let's say you have 50 numbers or hundreds of the generators, right? And whenever you have several large number of generators in the system, and you have to apply the active power control or the frequency regulation principle, then it is not the all the generators which will be in action. All right, it will not be all the generator. You will have the governor action only on selected generators. It is not all the hundred number of the generators will have the governor action, and thereby minimize the mismatch between the generation and the demand. In principle, normally we have the frequency control regulation, I mean, being applied only for selected generators to meet the demand here. And you can say that I think earlier also I have said that in the governor, one is you have the inner loop, and that is the primary speed control loop, which will adjust in each generator unit. So primary speed control through the governor will be in each generator unit, but supplementary control will not be in each generator unit. It will be only on selected generator units here, and it could be for a large generators in a given area here. And it this second the outer loops, secondary control loop or the supplementary control loop, they will be at the central control center, which will allocate the amount of power generation to a selected generator. So supplementary control loop, it will be only on selected generator among the several generators in the system. Okay, right? Anything? So we move. So here I have one slide to, I got it from the internet. I'm not sure if you are aware of how we have the governor action, and you can in this it is just an animation to show you how we apply a throttling on the turbine. So let us say that you have a load increase, right? So if you have a load increase, it means you need more power to be generated, right? And if you want more power to be generated, then in that case, you need more steam inlet or water inlet to the turbine, right? So when we have a load increase, all right, because suddenly load has increased, then frequency will drop. All right, the speed of the shaft will drop. So here we have a fly ball, and this fly ball is actually mechanically coupled to the shaft of the turbine generator unit. Because of the drop, because of the drop in the frequency and thus the speed of the shaft, this fly ball will move inwards. All right, because there is a drop in the frequency, these fly balls will move inward. This is, you can say, by the action of centrifugal force. So because of the drop in the speed, so this fly ball will it will fly inward. All right, and as a result, this lever moves down. All right, and then this point, lever point, will cause a uh, movement of the piston downward. This piston moves downward here. So when the piston moves downward, this inlet opens, because here you have a oil sump which will pump the oil from the sump to this side of the cylinder, that is the pilot valve, you can say, or sometimes we say control valve. So because of the pumped oil in this section of the cylinder, uh, the oil is filled in this duct here, in this side of the duct, right? And when the oil is pumped to this side of the duct, which will be at a high pressure, and as a result, uh, this piston in the cylinder will move to the left hand side here. It will move to the left hand side, and as a result, the sphere uh, on the nozzle point, actually this is the nozzle point, will move to the left hand side, and thereby the opening of the nozzle is increased, and thus the more steam will flow to the turbine blades, you can say. So this is the mechanism that we have for uh, you can say for hydraulic mechanical governor, basically, right? To regulate the amount of steam flow or steam inlet to the turbine section, you can say. Okay. Now, can anybody say if there is a load decrease, what will be the movement of the sphere?
Right side.
So it will move rightwards.
Outward.
So in that case, when the load has decreased, so the RPM will increase, right? Speed will increase, and as a result, this fly ball, will move outward. They will move outward, and thus this lever will move up, and as a result, you can say that this side of the piston will move up, and then the oil will be pumped to this portion of the control valve, and it is pushed here, this one, this side of the relay cylinder, and then this piston will be pushed to the right hand side, and thereby the opening here, in fact it would be the closing of the throttle, uh, right, and thereby decreasing the amount of steam inlet to the turbine, so that the amount of generation can match against the reduced load demand. Okay, so this is the action of the hydraulic mechanical governor, and here I have one picture to show you the fly balls, and this, and then there could be different spare shapes here as shown. Now, what is the basic purpose? What is the basic function of a governor on the turbine? Mainly, it is meant to vary the amount of power input so as to match against the demand here, and thereby maintain the frequency change. So that means contain the frequency change means maintain the frequency variation. And again, in addition, for the grid connected, when you have several generating units and then several power plants, then these governors can also be meant to have a parallel operation so as to achieve a sharing of power among the generators against the load changes. So whenever you have a load change, so uh, how does the generators will share the power to the demand? That can also be achieved through the governor action. It is not just to vary the output power, but uh, the parallel operation of the generators, and thus the sharing of output power of the generators against the load demand, that can also be achieved with the use of governor here. And so thus in a primary control way, we can say that these governors, they are meant to maintain a balance between the generation and the demand. So as shown in this figure, you have the turbine. So this is a steam inlet. So here you have a valve, and this is your governor, and you have a reference speed to the governor. And there is also a feedback signal, that is of measured signal, measured speed signal from the shaft of the generating unit, and this generator is connected to the grid here. So thus the in a primary function way, you can say that the governors will maintain a balance between the generation and the demand here.